Hello and welcome to our session today. My name is Temba. Today we're exploring current, in the context of electric circuits, in the broader knowledge area of electricity and magnetism. But we'll zoom our attention into understanding, the concept of current, right? Remember, we by now most probably familiar with the fact that there is, energy involved in as far as the circuit is concerned. We think of the battery as the primary source of energy. So the transformation of energy takes place throughout the circuit. So our discussion on, the bolts and nuts or the detail around the idea of current will be in the context of an electric circuit, right? So let's look at the overview in terms of where we are. Okay, so what do we know? We know that the battery is the primary source of energy, okay? So the battery provides energy for every coulomb of charge in terms of moving, charges in the external circuit. We also know that EMF is actually the maximum energy that a battery can supply, for every coulomb of charge. Now, in as far as, current is concerned, we know that current is transmitted through materials which we would describe as conductors. So what are conductors? These are metallic, materials that allow charge to move through them. And then insulators will actually do the opposite of conductors. These are the type of materials that do not allow electric charge to move through them. So insulators are essentially, bad conductors, while conductors are materials that allow charge to pass through, right? So the concept of current will be discussed in electric circuits, right? Now, the thinking that is going to guide our session for today are the following. Okay, have you ever thought about, number one, why is an ammeter always connected in series? We'll talk about an ammeter as a device that is actually used to measure current in a circuit. And then the second thought that you must think about it, okay, just to guide, our understanding, is that what does the ammeter reading tell us about how much charge moves in a circuit? So the ammeter is actually is the device that measures current, and then the reading that we get from the ammeter, what more does it tell us in our understanding of what current is all about, right? Okay, now the keywords, the terminology, very, very important. One has to emphasize at this point that whenever we talk of definitions, our point of reference becomes the examination guidelines. Keywords must be used in the correct context, and furthermore, we are saying that the definitions, which forms part of the language, is actually an all or nothing kind of an arrangement. It's either you know your definitions or you don't. But beyond reciting and memorizing the definitions, we also need to understand. So our lesson focuses on the understanding. That's why we emphasize on the thinking, how you must think as a young scientist, right? So current is the main concept for today, which is a quantity, okay? Remember, a quantity is anything that can be measured, because in the context of current, we'll talk about moving charge, either positive or negative. Think about the subatomic particles, okay? So when you talk about charge, think about the subatomic particles, all right? Okay. Now the subatomic particles are actually your protons, electrons, and neutrons. And then when we talk about current, we're talking about the electrons, okay? And then the word rate is used in many scientific contexts, as you discover as we move along. When we talk about rate, it has a component of time. So when we talk about the rate of something, let's say for argument's sake, rate of moving charge, we are asking ourselves, how much charge moves past a point in a given time? So the unit of time, again, very, very important, is a second. So if we talk about a unit, we're talking about one. Okay, so if we talk about a unit of time, what are we referring to? We are referring to 1 second. Okay, so the rate has a lot to do with time or time interval, okay? The change in time, all right? Okay, and then by now, we most probably familiar with the key components of a simple electric circuit from our earlier grades. We understand that for us to set up a simple circuit, we need certain instruments or certain components that make up that electric circuit. But the main idea behind a circuit is just to say to us that, look, energy is transformed from one form to another, as we know it from our background that energy cannot be created or destroyed. So it means that there must be, some form of energy converted or transformed to the other. So a circuit, as an example, says to us that energy is actually converted from one form to the other. So in constructing a circuit, we need a certain, components. What are these components? We need a cell. By now, we know that a cell is just a single unit with a pair of terminals, positive and negative, which is obviously going to be connected to a conductor, okay? And then a battery becomes a combination of cells that are connected in series, 2 or more. Then we have got a battery. So a cell or a battery becomes the primary source of electrical energy, okay? A conductor, we've spoken about it briefly to say that what a conductor does, it's a material in terms of physical properties that allows charge to pass through. So if we talk about electrical conductivity, we're talking about materials that allow electric charge to pass through them, as opposed to thermal conductivity, which has a lot to do with heat under physical properties of materials. So materials that allow charge to actually pass through them justifies even their use in everyday life. You think of copper wire, a nichrome wire, stainless steel. Most of them are used as electrical conductors in, circuits in our homes, because circuits, they just are not confined to, the small circuits that we construct in our school labs, but even beyond, outside the classroom, there are a lot of practical applications of electric circuit, which is the big idea of why we have to understand the science behind it, right? And then we also have a light bulb, okay, that represents a single light bulb, which also is connected to a conductor in a typical circuit. And then we've got a closed switch, okay? Okay, in a closed switch, actually, it says to us that current will be flowing, and then this is a broken switch or an open switch. So if a switch is open, it means the circuit is broken. It means there is no current in the circuit. Once again, let's look at how exactly we set up a simple electric circuit. What do we need for an electric circuit? We need an energy source, in this case, which is a battery, okay? Now, this is a cell in a way. Why are we saying it's a cell? Because there's only one unit, okay? But if we have got multiple of them connected like that, it becomes a battery. So for a change, let's talk about a battery, okay? This is a source of electrical energy, okay? Now, we've got conducting wires, okay? These are materials that allow electric charge to pass through them, okay? We will connect another one in the opposite terminal of the battery, right? And then we can have our switch. We will use the switch to complete or break the circuit, depending on whatever we need to achieve, right? Okay, we still have our conducting wires, which most probably it looks like a copper wire, okay? And then we can have another one, okay? And then we can also have a light bulb, okay? Just to show the energy transformation that takes place, okay? There is our light bulb, and then we will complete the circuit by connecting another piece of conductor. So that's our circuit. As it is now, the circuit is broken. What does it mean? The charges are there in the conducting materials, but these charges are not moving. Why? Because charge can only move once the circuit is complete. Okay, as it stands, the circuit is broken because the switch is open. But the moment we close the switch, okay, this is what is happening. Charges are moving. The battery provides energy or transfers energy to each and every charge such that they move through the circuit. But when these charges, which have got electrical energy, reach the light bulb, what is happening? There is some energy conversion. That electrical energy is actually converted to light. As you can see, the bulb is glowing. Okay, so if we break that circuit, the light energy ceases to exist, because that energy can only be there once there is electrical energy, which is transformed by the light bulb into light energy. So this is how we set up a simple circuit, right? So all these components that we have listed, your battery, your switch, your conducting wires, your light bulb, are the basic components that you need to set up a simple electric circuit, right? Okay, now, so these are the symbolic representations of the different components that we might have. So in this case of the, the simulation that we just showed, we have got a battery instead of a cell because we had a combination of two cells connected in series. Okay, we'll talk about that more as we go along, right? And then the new thing here is an ammeter. Okay, the new component that we have introduced is the ammeter, which is used to measure current. Okay, so an ammeter, this is how we represent an ammeter in a second. We'll connect the ammeter, obviously, at a point in a second, just to determine how much current passes through. So the measurement of current is done by the use of an ammeter, right? Okay. Now, let's talk about electric current, which is our main concept for today. Electric current is defined as the rate of flow of charge. Okay, the word rate has come up. Okay, that's our first encounter with it. When we talk about rate, we are saying how much charge passes through a point in a given time. So if we talk about a rate, we are saying, let's say for argument's sake, we talk about 5 coulombs of charge passing through a point per second. So the rate is 5 per second. That's the idea of the term rate. So the definition of current is incomplete without the keyword rate, right? So the symbol for current is I, okay? Which is derived from current intensity, which is an indication of what is the intensity of charges flowing through a point per unit time. So the SI unit is the ampere, which is the capital letter A, okay? Right, and then by mathematical representation, we know that current is amount of charge that passes through a point in a given time. Then it takes us to the mathematical equation I is equals to Q over delta T, where Q represents charge, okay? This charge is obviously electrons, okay? We know from conservation of charge. So then charge is measured in coulombs, right? While time is measured in second. This is the time interval, okay, through which a certain amount of charge passes through a point. So time is in seconds. Then the SI unit, by definition, when do we have an ampere of current? These are important questions in terms of understanding that we need to ask ourselves. When do we have an ampere of current? Understanding that current is rate of flow of charge, or how much charge passes through a point per second. So if we talk about an ampere of current, we are saying that there is 1 coulomb of charge passing through a point for every second, right? So if we talk it in terms of electrons, we know from quantization of charge that charge is equals to the number of electrons multiplied by the elementary charge. So if we have got a coulomb of charge, how many electrons must pass through a point per second? Now we can determine the number of electrons that must pass through a point, which is Q, in this case it's 1 coulomb divided by the elementary charge, which is 1,6 times 10 exponent negative 19. Here we want the number of electrons, okay, as per the principle of quantization of charge. Let's check how many electrons make up a charge of 1 coulomb so that we better understand this. Right, so in this case, we've got 1, okay, divided by, what do we have? 1,6, okay, times 10 exponent negative 19, okay? What do we get from that? We get 6,25 times 10 exponent 18, okay? This is 6,25 times 10 exponent 18 electrons, right? So in other words, what do we mean? We are saying that for us to have an ampere of current, there must be that number of electrons passing through a point in a conductor in 1 second. Okay, so we're trying to link what we already know to the new knowledge. Now, having said that, let's understand that current is the rate of flow of charge. If we break it down to make it simpler, we are saying, let's ask ourselves, if we have a reading of current, what exactly are we talking about? If it's an ampere of current, it means there is 1 coulomb of charge passing through a point for every second. Equivalently, if we have got 10 amperes, it means there's 10 coulombs of charge passing through a point in a conductor for every second. After a short break, we'll talk about how exactly we measure current in practice using our device, which is the ammeter. Let's take a short breather for now.